Okay, so the next question is find this value k to make this finite length sequence, W of n, periodic conjugate symmetric. So whenever you see periodic conjugate symmetric, it means you're dealing with a waveform that begins at n equals 0. And to find the part that's conjugate symmetric, we're going to take the periodic conjugate extension. And that just means replicating the signal. Over and over in both directions. Now, practically, we could continue to replicate it on the left. And we could continue to replicate it on the right. But to get the information we need, we just need to go to the left as far as we are on the right. So it's 1, 2, 3 on the right. So it's 1, 2, 3 on the left. So this is the part that we care about. And we need to find what value of k will make this entire signal periodic conjugate symmetric. So another way of saying that is we have to have these items align, and we have to have these items align, and we have to have these items align. So what needs to be fixed with k in order to make these things the same? We don't need to do anything with 9. 3 minus j. And when I say align, what I mean is that these have to be the complex conjugates of each other. So k has to be the complex conjugate of 3 minus j. So that would be 3 plus j. So we've taken care of the red. Let's say the green, that's already its own complex conjugate. That's okay. It's real, so -1 is its own complex conjugate. Yellow, 3 minus j has to be equal to k complex conjugate. But I think it's pretty clear that if this is k, then this relationship is true too. So therefore, the answer is k has to be equal to 3 plus j. Now, if you want to see why that's, if you want to take a mathematical approach, you could instead, you could check our work and say our new omega n is equal to 9, 3 minus j, minus 1, and 3 plus j. And let's see what the periodic conjugate symmetric portion of this waveform is. So we're just going to check our work here. And the periodic conjugate symmetric portion of this should be the original signal if the original signal is periodic conjugate symmetric. So we could do it graphically, and we'd end up drawing the exact same graph here, so that's not very interesting. Just to be different, I'm going to do it mathematically. So I'm going to say it's equal to, so it's equal to W of n modulo capital N plus W of minus n modulo capital N. So for this particular example, we see n is 4. There's 1, 2, 3, 4 elements of it. So therefore, n equals 4. And so let's evaluate this for a few different values of little n. So I'll say, what is the first value? We're going to just set n equals 0 in this above equation. So that's the same thing as 1/2 W of, now we want to say 0 mod 4. So in other words, we want to add or subtract multiples of n to bring our number from wherever it was to the region of 0 to 1 less than that capital N. So I'll just write this down. And I'll immediately write down what the answer is. 0 mod 4 means we have to add or subtract multiples of 4 to 0 until we bring it to the range of 0 to 3. Well, it's already in the range of 0 to 3. It's 0, so that's just the same thing as W of 0. And then to that, we're going to plugging in our n equals 0. We get this, but that's just the same thing we already worked out as W of 0. So that's the same thing as saying 1/2 of, let's see, what is W of 0? W of 0 is 9 plus 9, and so that's 9. So the conjugate symmetric part of 0 is 9. The original signal at 0 is 9, so that works out. Let's try the conjugate symmetric part of 1. That would be 1/2 times W at 1 mod 4 plus, I forgot to put in the conjugate signs here. Makes no difference because so far values have all been real, but now it's not going to be real. We're going to have the conjugate value of, let's see, negative n. So if n is 1, this will be equal to negative 1 mod 4. All right, so let's do the modding operations. 1 mod 4 means we can add or subtract multiples of 4 to bring this number into the range of 0 to 3. It's already in the range of 0 to 3, so we're done. This says negative 1, add or subtract multiples of 4 to bring it into the range of 0 to 3. We add 4, and we get 3. So now we can plug in our numbers. W at 1 from our sequence is 3 minus j plus W star at 3, 0, 1, 2, 3. This is 3 plus j, but we need to take its complex conjugate, so that would be 3 minus j. And now when you add up the 3 plus 3, you get 6 minus j2, and that's 3 minus j. And let's check. Is the conjugate symmetric part at 1? If it is 3 minus j, the original signal is also 3 minus j. So far, conjugate symmetric part does match our original, and we can continue on this for WCS at 2 and WCS at 3. We'll see it matches our original, W at n, and so then we can show that WCS equals our original, and now we can be even more sure that this is the correct answer.